So welcome to the second part of wave equations. Here we'll be looking at some numerical considerations, working with the progressive wave equation. Then I will introduce you to the two-wave equation, which I said the equation for standing or stationary wave. Then we look at examples of 2D and 3D waves. Now look at an example. The question says a plane progressive wave is represented by the equation y equals 0.5 sine 150 pi t minus 5 pi x over 4. Close the bracket. Okay, now said, and that's a very important instruction, that the displacement is in millimeters, while the distance from the source is in meters and the time is in seconds. Now estimate the following: the amplitude, the frequency, the wavelength, the speed of the wave. Then what will be the phase difference of an oscillating particle or wave between a point 0.125 meter from the origin and another point which is 0.5 from the origin, also between the point 0.125 and 0.75, and also between a point 0.125 and 1 meter. Okay, very easy to attend to. Let's do it. First thing to do is to write out the equation. Write out the equation. The equation is this. We now look at the equation, general equation given to you previously, the one that is closest or that is identical to this. And if you search through, you discover that it is this one. Now, mind you, you must write that equation as. So if you is given as plus in your question, then you have to put a plus here. If the function of x comes first and this one comes here, likewise you rearrange it. 2 pi x over lambda, you bring it here. 2 pi ft, you bring it there. Okay, you must arrange so that it will be easier for you to handle. Okay, so the question says estimate the amplitude. Remember, the displacement is in millimeters, therefore the amplitude will be in millimeters. So and from there it's 0.5 a is 0.5 millimeters. Now you may now convert to meters, which will be 0.005 meters or 5 exponential minus 4 meters. Then you can also obtain frequency. How do you do that? Compare the expression here where you have your frequency f with 150 pi t. Equate. T cancels out. So you have f. So 150 pi divided by 2 pi. You have 75. And the unit of frequency is hertz. Then estimate the wavelength. Also wavelength, you compare this equation 2 pi x over lambda with what is given in the equation 2 pi x over 4. And when you solve, x cancels l. Likewise, your pi, you cancel your pi. So your lambda will be 1.6 meters. Remember, the distance is in meters. That's why your lambda is in meters. So again, amplitude assumes the unit of displacement, but wavelength, velocities, wave velocity, wavelength, wave speed assume the unit of the distance, and the frequency is determined by unit of the time. Frequency and period, unit of the time that affects them, are determined by the unit of time. So your wave speed is equal to f lambda. So we have 75 hertz in 1.6 meters, and you have 120 meters per second. Remember, hertz means per second. Anywhere you see hertz, h is it, then it means per seconds. So if unit is given in per minute. You cannot say your f is hertz. If time is given per minute, cannot be, you must convert to seconds for you to get your f as hertz. Okay, if time is in minutes, any other unit apart from seconds, then unit of f will never be hertz. You must convert first to seconds to now assume that your unit of frequency is hertz. Then the phase difference. Phase difference 2 pi over lambda x2 minus x1. Remember, we said it can be, let me just write it, the full expression 2 pi over lambda x2 minus 2 pi over lambda x1. Okay, so here now this is our x1 and this is our x2. So x1 is 0.125. In the first case, x2 is 0.5. In the second case, s2 is 0.75. In the third case, s2 is 1 meter. Once you check it, so you go, your phase difference 0.75 minus, we'll put it there, area first 0.75 minus 0.125. Estimate. So the phase difference is 1.25 pi over lambda. Where you can now substitute the value of your pi, which is, or your lambda, which is 1.6 meters, and to obtain your value in terms of pi. Or you may want to also substitute the value of your pi 22/7. You take your answer in radians. Okay? In radians. Or use your pi as 180 degrees and obtain your answer in degrees. Okay? Likewise, you have 1 and 0.125. Also, the first case 0.5 and 0.125. The answer will be 0.75 pi over lambda. For 0.75 minus 125, we have 125 pi over lambda, and the third case we have 0.175 pi over lambda. So that's where you can put the value of pi and lambda. Your pi 22/7, that means your answer will be in radians, or 180 degrees, your answer will be in degree. Okay?
So we have another example. In this example, you have y equals 5.0 sine open bracket 0.03x plus 8.0t. I will say x and y are in centimeter. That is, the distance is in centimeter. The distance traveled by the wave, propagating wave, or progressive wave, is centimeters. Then the displacement of the particle is also in centimeters, and your t is in time, is in seconds. So you have to calculate the amplitude, the wavelength, the frequency, wave speed, or that's the wavelength of the wave, the frequency of the wave speed, the wave velocity of the wave, the direction of propagation of the wave. That's you have been considering the Cartesian coordinate, and also the maximum transverse speed of the particle. Now, this is not the speed of the wave now, not the wave speed, but the particle speed, the displaced particle, the vibrating particle itself, such as the string, the speed, maximum speed with which it oscillates. That we have to look at. So you have the equation y is this. So you look for a very close on the list of expressions given earlier in the last video. You look at the list and you compare. From here you see that the amplitude A is 5 centimeters. Next, we want to determine the wavelength. So you compare this equation 2 pi over lambda x with 0.03x. You solve that the rearrangement now. Omega t is coming at the second term, where 2 pi over lambda is coming at the first time. So you have to rearrange in line with how the question was presented. That's for ease of operation. You can do without that, but for ease of operation. So you have our expression. So you equate that x cancels x. Your lambda will be 200 pi over 3, which is 66.67 pi centimeters. You can put that pi into 2 over 7 and get your answer in that expression. You can also leave it in terms of pi. Then for the second one, the frequency, omega is equal to 8t. So t cancels t. So your omega is 2 pi f. So please make f so your formula. Your answer will be 4 over pi x. Also put your 2 over 7 and solve. I'll leave it that way. Then the wave speed or wave velocity is f lambda. So what you have as your f and what you have as your lambda, put it there. Lambda cancel lambda, you have 800. Sorry, pi cancel pi, you have 800 over 3. That's 803 centimeter per second. So about 3 centimeter per second. Then you have 5 is to determine the direction of vibration of the wave. To do that, you equate the phase angle to 0 and you solve. You separate the other side of the equation of the equality sign and you make x over t, so your formula. And x over t is also velocity. So x over t, your formula, you equate them, divide both sides by t at this point. Divide both sides by t. So you have x over t here, which is equal to minus omega lambda over 2 pi. So this minus sign shows that the wave is moving in negative x direction. And if you substitute the values you have obtained earlier for omega, for lambda, then you discover that we also obtain the same expression that we obtained, which is 800 over 30 centimeter per second. Okay, so you can try that and see. We have 800. Remember our pi is our omega is 4 over pi. Sorry, is 8. Our omega is 8. Sorry, I was going to help again. Our omega is 8. Then the lambda is 200 times 200 times 200 pi over 3. Then everything to pi. So you see, pi we cancel pi. 2 we go in 200. That's 100. So you see you have 800 over 3, which is as what we have earlier. In our figure 4. So the negative sign there shows the direction which the wave is propagating. Now the next question is to the maximum transfer speed for a particle on the string. The maximum transfer speed for a particle on the string. So we have the displacement of the particle differentiated with respect to time, give us the speed of the particle. And if you differentiate the equation y, differentiate it, equation y, you have the expression. Okay, you can do it this way and do it any way you want to do it, no matter what you want to do. Okay, so if you differentiate this, y is equal to a sine 2 pi open bracket 2 pi over lambda x plus omega t close the bracket. We have the expression omega e cos. Then the maximum speed is obtained when the cos of your phase angle is equal to 1. So when the cosine of the phase angle is equal to 1, then you have your maximum speed. So in that case, we just work with omega e, and we know our omega already. Angular frequency, which is 8 meters per second. And then the amplitude is 5 centimeters. So the answer will be 40 centimeters per second. So you see it's clearly different from the wave speed. Clearly different from the wave speed. Okay. Another example. A longitudinal wave propagates along a slinky spring when a vibrator attached to one of its ends vibrates at 20 Hz. If the distance rather between the two successive compressions along the spring is 18 centimeters, estimate the wave velocity. 2. If the maximum longitudinal displacement of a coil of the spring is 0.25 cm, as the wave is propagated along the positive x-axis, and assume that the displacement at t is equal to 0 is 0, write the wave equation in the following form. Now, this is interesting. I want to be attentive again. Now, a longitudinal wave. Longitudinal wave, instead of having this transverse wave, we have this for that transverse wave. Here we have longitudinal wave. We have series of refraction and series of compression. You have compression, then you have then you have compression. So distance between two compressions or distance between two refractions is like distance between two crests or distance between two troughs. So in that case, we also refer to it as one lambda, one wavelength. So therefore, if the distance between two successive compressions along the spring is 18 centimeters, that means we are talking about the wavelength is equal to 18 centimeters. And it is said that the frequency of the source of the oscillation, and we say frequency does not change as the wave propagates. So if the frequency of what causes that vibration is 20 Hz, then the wave will also have a frequency of 20 Hz. Okay? The wave carries the frequency of the source. So 20 Hz. 20 Hz. Okay, now all with the velocity. So very easy. Now that you have f, you have lambda. The velocity is v f lambda. Is that not? So straight away you get your answer. Straight away. Now the question now says, if the maximum longitudinal displacement of a coil of the spring is maximum longitudinal displacement, that is distance from the rest position to the peak compression, or from the which is like distance between equilibrium position and the peak crest or peak trough, which is amplitude, is 0.25 centimeters. What they are saying is your amplitude is 0.25 centimeters, and the wave is propagated along the positive x-axis. Please note that too. Positive x-axis. Now, write the wave equation in the following form. Now, in this following form, our A is known already. So consistently, for this expression, our A, we can get our A. For this expression, we can get our A. Here we can get our A. Then, omega can be obtained. Is that not? 2 pi f. That's omega. You can obtain it. Then lambda is known. So straightforward. If that one is settled, then also f is known. Lambda is known. Also obtain this. Here with our f, you can obtain your t. Is that not? Then that was also known. And also we know our v. Or now our lambda. That is also known. So just substitute it. You see the next slide. That's what I just did. So in that expression, just get it. So you just substitute in a different expression and get this. So in this case we have this. I simplify. That's why I have pi over 9. Just be 2 pi, just 2 pi over 18. But to simplify it, you have pi over 9. Likewise here, I can leave it as 2 pi over 18, but I simplify to have pi over 9. I have that expression straight away. Straight away. Where displacement is centimeters and distance is centimeters. That's as given the question. Okay? As you have seen, generally that wave equation can be, or waves can be expressed by a wave function. Usually they use y. Although as at higher level as you go on, you see other ways of representing the wave function. Instead of using y, you can use fs, you can use phi, you can use many things. But in this case, you are using y as a function of x and t, distance and time, displacement. Okay? But if you're not giving a wave function, how do we now know if such wave function represents a progressive wave or representing a stationary wave? How do we know? How do we know? Now, that's where the two-way wave equation comes into play. And it is given as what you have here. Second derivative of displacement with respect to time equals the product of the speed of the wave and the second derivative of the displacement with respect to distance traveled by the wave. Okay, so if this expression is true for the wave equation, then such a wave is said to be traveling or progressive. If this is true, if you subject your wave equation into this expression and it is satisfied, if that wave equation wave expression satisfies, or wave function satisfies this two-way wave equation, then such a wave function or a wave expression is said to represent a traveling wave or a progressive wave. Otherwise, then such represents a stationary wave, and this is called the one-dimensional. One-dimensional just in terms of the x direction, the x plane. That's why we have x. You see it? So the direction of the wave is just in one plane. In one direction we have x. And you can also rearrange it as the second derivative of displacement with respect to the distance equals to the product of the inverse of the square of the wave speed and the second derivative of displacement with respect to time. I can always confirm if you have written right, so that we will not write this one, this first one, and now put 1 over v square here, and this one now put v square. How to confirm is that just look at it. V squared is d square x dt square. Is that not? Say v squared is d square x. That's my one hint for you to confirm. D square x dt squared. Dt squared. Now with your d square y, d square y, dx squared. You see, that means they cancel out. Almost, that's not correct. It should be dx squared because b is equal to dx dt. So it should have been d dx dt dx dt squared, dx dt squared, then d square y dx squared. And if you now open the bracket, you have dx squared, then dt squared, then d square y, then dx squared. So dx squared will cancel out. you have what you have on the right hand side, since I also have on the left hand side. So that's how to confirm. If you do for these two, you have the same thing. That's how to confirm whether your variety is correct or not. So if you subject your wave function to this expression, you can now determine if this wave function represents a traveling or progressive rate or stationary or standing wave. And again, that represents a one-dimensional wave equation. So for a wave function representing a wave in 2 dimensions, such that we have the wave traveling in 2 dimensions, x and y plane. In this case, we use r to represent the wave distance traveled by the wave, because it's no longer in 1 dimension, it's in 2 dimensions. Okay, let me just show you that how they got that. Okay, it's now in 2 dimensions, x, y. Okay, in 2 dimensions. So what will be your r? This is your r. Your r in this case now, using Pythagoras, will be r squared equals what you have, x squared plus y squared. Okay, and that's why we are using f to represent our function. So I said f may be used to represent the function, it may be y, it may be anything. In the 2 dimensional, because we have introduced y as also, in this case now, y also represent distance, but in the y plane, the y dimension. So we are using our f to represent our function. Okay, so in this case we can see f is a function of x. So using r times, you see the right to x, comma y, comma t. Okay, so you have this, and that general expression can be, for the wave equation, can be expressed just like it was d square y dx squared, this. So in this case now, we just put the square f dx squared plus the square y dx, because it's now in 2 dimensions. So that is, and that's very similar to what we have here. We have d squared y d, that's not equals for the 1 dimension, equals 1 over b squared d squared y over dt squared. Okay, so very very similar, just that in 2 dimensions we now use f a function of r and t, and r is a function of x and y. So we just have to do that. Okay, and in that case we can now use this to represent d squared dx squared plus d squared dy squared. Okay, if the wave, 2-dimensional wave, is circular symmetry, it's a perfectly circular wave, perfect circular wave. Okay, perfect circular. Maybe the water wave is perfect circular wave, or water wave is more of 2-dimensional wave. Then instead of using the expression, then we make use of this expression. Okay, so just function of differentiating and substituting. And if the radius of such a circular wave is so large, maybe water wave on a water body, maybe on an ocean, okay, so large, then the expression in equation 15 is reduced to this expression. Okay, reduced to that expression. So So in this case, when the wave is propagated and is going in the x, y, and z plane, such a wave is said to be three-dimensional, where this function represents such a wave depending on the distance traveled by the wave, which is in three-dimensional x, y, z, and the time. Okay, and r is obtained in this expression. Example, if you have your x and you have your y, which are perpendicular to each other, you can get, okay, you can get this. Let me call, can I call this? Let's call it a. So you now have a. They now have z now. So for now, to get r now, is a function of also perpendicular to each other, a and z. Then you have your r. That's how to get three dimension. A in this case is square root of x squared plus y squared. So if we put a here to be square root of x squared plus y squared, then you now cannot get your r, which will now be what? Or which will be r squared, which will be a squared plus z squared. And when you do that, you obtain this expression. Okay, that's three dimension. Okay, but if it were to be a sphere, that's when our heads now consider all this expression. We have a perfectly spherical wave, three dimension, perfectly spherical wave, three dimension. Okay, and that's when you have a spherical wave in three dimension. So you have this expression. Okay, and which is simplified for a large radius. Simplify with this expression. Okay, where the Laplacian operator is represented as this. I'm just introducing you to this at this level. For those at higher level, you will relate more with this. Some of these are equations or expressions. At this level is also familiarize yourself with them. So when the Laplacian operator operates on the function, on the wave function, and what you have is also equal to what you have on the right hand side, then we have a progressive three wave equation. Okay, so those are what the Laplacian operator represents in 2D and 3D. For a spherical, perfectly spherical wave in 3D, you have this expression. Okay, we have examples of three-dimensional waves. Sound waves in air, ocean waves, which is beyond the surface, those deep into the water body. The electromagnetic waves in space. The earthquake P waves and S waves. Unlike the seismic wave, the P wave and S waves travel through the earth crust itself. Okay, and we have waves in solids. Solids are three-dimensional, so waves through there also will be three-dimensional.